AQA A-level physics. This is for the medical physics option, and this video is about eye optics, the optics of the eye. Now this ray diagram, you should recognize this from GCSE. You did quite a few ray diagrams at GCSE. This is the only one that I'm interested in now. We have an object, we have a lens, a convex lens. This dot here, that's the principal focus, it's called, the focal point of the lens. The distance from the lens to that is the focal length. And then over here we have an image. Okay, so this ray diagram, this is for an object which is more than 2 focal lengths away, and this forms an image as shown here. This kind of may make a bit more sense to you. We have an object which is a candle. The object distance, we're going to call that u, little u. Yeah, that's the distance between the object and the lens. The image distance, so what you do is you move the screen until you get a focused image, and then the image distance is v, so little v. So you've got little u is the object distance, little v is the image distance. Notice 3 things about the image. It is a real image. That means it's an image that you can project onto a screen. It's not like what we call a virtual image, like if you look in a mirror, that's a virtual image. It's a real image. It's inverted, which means it's upside down, and it is diminished, and that means it's smaller than the object. So a real inverted diminished image, and remember little u and little v, because this is the lens equation. Okay, this is the relationship between u, v and f, where f is the focal length. Okay, so 1 over u plus 1 over v equals 1 over f. We'll have a look at an example using this equation on the next slide. There's another equation we need to know. P, big P, is 1 over f, and big P is called the power of the lens, and power of a lens is measured in diopters. A convex lens, or a converging lens is another name for it, has a positive power, and a concave lens, or a diverging lens, has a negative power. Looking at the convex lens, if you had parallel rays of light coming in, they would converge. Yes, if the rays were parallel coming in, they'd actually converge at the focal point. Okay, and that's a positive power. And then the concave lens, 3 parallel rays would diverge like that. Okay, so this has a positive power, this has a negative power. Again, we'll use this equation in a bit. With this equation, one important thing is that the focal length needs to be in meters. If you want the power in diopters, then the focal length has to be in meters. With this equation, it doesn't matter. Everything, as long as everything's in either meters or centimeters or whatever, as long as it's the same throughout, it doesn't matter. And then one other equation is for the magnification. And the magnification is the size of the image divided by the size of the object. If the image is diminished, then the magnification will be less than 1. And in the case of the eye, it nearly always is diminished. Okay, so the magnification is the size of the image divided by the size of the object. Do you want to have a go at this by yourself? Pause the video, pen, paper, calculator, get it done, and I'll show you the answer here. So a lens forms an image of a 22 centimeter tall cat 50 centimeters away. So u is 50. Yes, I'm just going to leave that in centimeters. U is 50, 2 centimeters from the lens. So v is the image distance, and that's 2 Okay, so 1 over f is 1 over 50 plus 1 over 2, so f is 1.92 centimeters, and then the power of the lens, remember that F has to be in meters, is 1 over 0.0192, and that's plus 52 diopters. Okay, the magnification is the size of the image. No, well, it's V over U. So V over U is 2 over 50, which is 0.02. And so the size of the image will be 0.02 times the size of the cat, which would be 0.4 millimeters. 4 times 10 to the minus 4 meters is the size of the image. Very, very small on the screen. Now, if this was an eye, then there's a few points to make here. The power is the combined power of the cornea and the lens. Remember that the cornea actually bends the light more than the lens does. So this is the combined power of the cornea and the lens. The power of the lens alone can vary, as we shall see, between plus 20 diopters and plus 33 diopters. Okay, the power of the cornea stays the same because that doesn't change shape. And by the way, this a screen 2 centimeters. Usually we take the diameter of an eyeball to be about 2 centimeters. I think on average it's about 2.4 centimeters, the diameter of an eyeball. Accommodation. I said that the lens can change shape. If you're looking at things close up, if you're looking at things far away, then the focal length of the lens can change, and that's because there are these muscles. The lens is made of a kind of a tough jelly, and you can stretch it and squash it, okay? So when viewing close objects, the ciliary muscles contract, and that squashes the lens, making it thicker and making it more powerful. So on the first diagram, we're looking at this cat, which is quite close up. And if you look at the lens there, it's kind of fat, and that's because the ciliary muscles are contracting. The closest that you can look at an object and still be in focus, and try it for yourself, just cover one eye, look at your finger and bring your finger closer and closer and closer to the open eye until you can't focus anymore. And for somebody with normal vision, a young person with normal vision, about 25 centimeters, and that's called the near point. You need to know that. The near point, that's the closest you can focus, is about 25 centimeters. When looking at things far away, distant objects, then the ciliary muscles relax, and so the lens becomes thin. Yeah, it becomes long and thin and less powerful. And the far point is the furthest distance that you can focus. And for a normal eye, we say that this is infinity. You can look at that, basically means you can look at things very, very far away and they'll still be in focus if you can see them. Vision defects. We need to know myopia. We need to know hypermetropia, and we need to know astigmatism. Myopia is being short-sighted, hypermetropia is being long-sighted, and astigmatism is a problem with the cornea, as we shall see. So myopia, this person is short-sighted. Now, short-sighted, they're trying to read, and you can tell a short-sighted person because they'll bring it close to the face to try and get it in focus. And basically what's happening is that the rays of light are converging short of the retina. Yes, so they converge short of the retina, and so that on the retina it's all not in focus, it's all blurred. The rays of light converge short of the retina, so the image is blurred, and basically the cornea stroke lens is too powerful. It's bending the light too much, it's refracting the light too much. This might happen if your eyeball is too long, or if your cornea or your lens isn't working properly. Okay, so how do we help this person? Well, you give them a pair of glasses, and in the glasses you have a concave lens. Okay, because the power of the lens and cornea is too big, what we do is we add on a little bit of negative power. So we give them a concave lens, and that will diverge the light a little bit so that after it's gone through the cornea and the lens, it will focus on the retina. So the total power of the system is reduced so that the image is now focused on the retina. Be able to sketch these diagrams. I imagine you'll be given the diagram of the eye, and you'll have to do the rays of light and talk about how the concave lens does its job. And that's short-sightedness. Hypermetropia is long-sightedness. And it's long-sighted. Now, you can tell a person here because they hold the book far away from their face to try and get it in focus. They're long-sighted. The rays of light would converge behind the eyeball, but obviously they don't have a chance to get there, so you just get a blurred image on the retina. The cornea lens is not powerful enough to converge the rays to a focus on the retina, so the image is blurred. This may happen when the eyeball is too short or caused by some problem with the lens and cornea not functioning properly. For example, as we get older, the lens becomes less flexible so that we don't accommodate as well. Yes, and that usually happens, well, it certainly happened to me. So this is long-sightedness. How do we help this person? Well, we need a little bit more power, don't we? So we give this person a convex lens. A convex lens has a positive power, so we are increasing the total power of the system, and so now the light rays converge on the retina and the image is in focus. Astigmatism. Now, this is a problem with the curvature of the cornea. Okay, for example, the cornea is asymmetrical. It's curved asymmetrically. Look at the diagram. Maybe it's kind of a bit shaped like a rugby ball, and that will affect the way light is refracted, and that will cause blurred vision. Okay, so it's kind of though we need some kind of correction, but only along one side axis, if you know what I mean. It can usually be corrected by glasses which compensate for the imperfection. And one thing you should be able to understand is if you get a prescription for somebody with astigmatism. Look at this prescription here, and there's two things on it I'm interested in. There's the axis and this cylinder here, CYL cylinder. Okay, we've got the right eye, we've got the left eye, and look, cyl or cylinder is the amount of correction needed in diopters. So here, looking at cyl, on the right eye, it's -1, on the left eye, it's -0.75, and then axis is the angle at which the correction should be placed on the glasses. So axis is actually a number from 0 to 180, or is it 360? Look it up, I can't remember. So axis is the angle at which the correction should be placed on the glasses, and cyl is the amount of correction needed in diopters.